Welcome to a lesson with Dr. Powell. In this video, we will look at an example of finding the volume of a solid resulting from rotating a region about a line, or in particular the line y equals 4, or the axis of rotation, and the region given in words here. I went ahead and drew what it would look like. But if we didn't know, we just have to step through it. Y equals 0, that's the x-axis. Y equals e to the x, that's an exponential curve. And at 0, it's going to be 1, so it intersects the y-axis. That's the y value at that point. And the y value when x is equal to 2 natural log of 2 is going to be 4. And you can see that because 2 times natural log of 2 is the same thing as the natural log of 2 squared by a log property, which is equal to the natural log of 4. And if you raise e to that, look, e and natural log cancel, it's going to be 4. Okay, so that's where we're starting. We have our region sketched out. And we want to use washers. So we think, do we draw our lines? So the region is in here. This is where the region is, all right? And we think, are lines that are parallel to the axis of rotation or perpendicular, when I rotate them around, going to look like washers? Well, if I did something parallel and rotated it around, say a line like that rotated around the axis, would result, you can kind of imagine, result kind of in a shell. That's not a washer. It's like a part of a can, right? Okay, so we're not going to use horizontal lines. What about vertical lines? Take a vertical line and rotate it around. Imagine what happens. This line swings around and goes around like this and around and around. And when the line swoops, you can kind of turn your perspective. So maybe this line y equals 4, you're looking straight down it with your eye. And what happens to a line that's being swung and rotated around as it goes around? It's what's going to happen is, as it moves around, it's going to trace out a region which looks like a washer. All right, so it's going to trace out a region that's going to look like a washer, that line, as it rotates around. And so that's what we're going to use for the washer method. Okay, so essentially, kind of the idea is we're going to get this shape that's formed by rotating around, and if we slice it at one point, determined where we are on this axis of rotation, these are x values, right? So at an x value, which represents a point on this line, okay, so at x, then we can find a washer area. Now, if you think about volume, increasing volume growth from here, right, as we keep on moving in this direction and adding on more and more of these washers, just kind of stacking them up from here to the end, that forefront of the growth, if you turn your vision and look right, if you were to like cut the piece and just look at it, this is what it would look like. You would see that cross-section area. This area right here is equal to the derivative of that volume growth with respect to x as we're moving along this way. So that would be like, we can say v prime of x. Now, and we're interested to know, and perhaps right here, and we're going to assume that the volume at 0 is 0. And we want to know what v of 2 ln of 2 is equal to. And we know the derivative of volume is just equal to this washer, the area of this washer. So in order to find the volume right here, what we do is we compute an integral, in fact a definite integral, going from this beginning point to here. To get the change, we want to get the change of the volume, because the volume starts out at 0. So the change of volume will be equal to the actual volume at this point. So this will actually be equal to the change of volume from 0 to 2 natural log of 2, since we're starting at a volume of 0. Okay, so this change of volume going from 0, which we could represent like this, 2 ln of 2 minus v of 0, which we can represent as an integral as we move from 0 to 2, natural log of 2, and then we put the derivative of the volume, right? Because, you know, this is like v is like the antiderivative, so we need the derivative of it, which is just the washer area, but it needs to be a function of x. Washer area dx, and that should be equal to the volume of this rotated solid. Okay, now all you have to really do now is figure out at a particular x value what that washer area is going to look like. You know, it's a washer. Let's just think for a minute. It's going to have a inner radius. The distance from the inner radius is just right here, right? From here to here. So you have to think, what is that? So think about like this vertical line right here as being like a number line or something, and you have different positions on it. You have the position y equals 4, and this guy, y equals what? Well, to add an x value, y equals, hey, the y value on this curve at an x value is e to the x, right? That curve's y equals e to the x. Okay, e to the x. So the distance from y equals 4, yeah, from y equals 4 to y equals e to the x, those are different. So think you have a number line, and you have like y equals 4, and then you have y equals e to the x. So you have like these two different points on a number line. How do you find the distance between them? You subtract them. 4 minus e to the x. So the radius right here is actually going to be 4 minus e to the x. And that's of the inner radius. Okay, so the inner radius is that. So how do you find the area of a circle with a given radius? It's pi r squared. Keep in mind, a lot of people, and maybe not you, but a lot of people get confused with these formulas, 2 pi r and pi r squared. They think it's some kind of magic thing, that one thing or whatever, and they don't really know rhyme or reason. But just, if nothing else, think of this. This guy is the derivative of that guy. And like, this is area, and the derivative of area is actually, you can think of it kind of at like length. I mean, think about like curve, and you know, you have increasing area. What's the derivative of increasing area? It's the length right there of the growth, the length. So length, so this guy better be perimeter or circumference, right? Okay, so if you want to think of that way, it's like kind of a quick idea. Hopefully that'll help someone. Okay, so to find we need the area of the circle, which is pi r squared, so the inner circle. And we're going to subtract that from the area of the outer circle to get the area of the washer. So maybe to kind of think about this, maybe to kind of, you know, maybe I should like shade this in so you can kind of see what happens. What I'm shading in right here is the area that's, or the region that's actually created by swooping that line through and rotating it around. Okay, I should have maybe filled it in earlier, but we'll just keep going. Okay, so that's that. But the inner radius, so this is this inner circle we're going to be subtracting. So the area of that. So we have, so the washer area, you're going to have the inner circle is pi times the radius, which is 4 minus e to the x squared. Okay, and that's at a particular value of x. Notice how the washer area is going to be a function of x, because it is the derivative of volume with respect to x. It's going to be a function of x. All right, now the area of the outer one, we got to find that. So, and sometimes it's nice to not fill this in, but I did it just so we can kind of see what was happening. But just so we can kind of draw things out in practice, but just remember that's the area that we're looking at is right in there. So the outer radius, how is that going to be obtained? Well, in the picture here, that's from this axis to this outer point. Well, that's kind of handy. It looks like it's constant outer radius right there. It's just, oh, this whole distance, we know what that is. That whole distance is 4. That's pretty simple. It's just what? pi times 4 squared. Okay, so that's our function right there. So it's what, 16 pi minus pi times, so pi times that squared, right? Yeah. So, and maybe we can multiply that out. All right, so if we square this, I'm thinking kind of a foil. You're going to get the first times first is going to be 16. And then you're going to have a middle and an outside term. Remember, you're foiling. You have another one of these factors right next to it. So you have an inside and an outside. So the outside, so basically, and they're going to be the same thing if you're squaring. It's essentially just this 4 times negative e to the x, but then doubled is what the middle term is going to be, which you end up getting, so minus 8 e to the x, and then you have plus negative e to the x squared, which is plus, because negative times negative is positive, and then e to the x times e to the x, but the exponents x and x add. So it's like e to the x plus x in the exponent, so it's e to the 2x. So there we go. Now, what have we obtained? That's the function v prime of x. We found the derivative. Great. That's what we're going to be integrating. So the nice thing about these types of thing is, it's easier to determine what the derivative of volume is than the volume. So, but if we can know how to take antiderivatives, we're pretty good if we can find derivatives, right? All right. So then, working this out, let's see what happens. Notice the 16 pi will cancel when this pi times 16 comes together. Okay, a negative pi will come over here to give us 8 pi e to the x. Negative pi will come over here to give us negative pi e to the 2x. And remember, we haven't taken an antiderivative yet. I'm just algebraically rewriting it. Okay, and perhaps I could even pull a pi out if I wanted to, or whatever. Okay, but we can take an antiderivative now. So maybe, let's just remember we still haven't taken an antiderivative yet. And maybe we can put this on and remember what the bounds are. 0, 2. In fact, I'm going to rewrite it as ln of 4. I like that better. Ln of 4, because that's, the 2 comes up right there, so it's the same thing. Because when I plug it in, it'll be nice. We've got to take an antiderivative first. What's the antiderivative of this function, which is the derivative of volume? So that would be 8 pi e to the x. The antiderivative of e to the x is just e to the x. That's great. And then 8 pi is just a constant multiplier on negative pi. What's the antiderivative of e to the 2x? Well, that's e to the 2x, but then divided by 2, and you can test it out. I mean, derivative of e to the 2x by the chain rule is, well, derivative of e to the 2x is e to the 2, e to the something is e to the something times the derivative of that is times 2, right? But if you had an extra 1/2 multiplier on, that would cancel. That's great. So that's why you have the 1/2 there, or you divide by 2. Okay, so that's the antiderivative. And then we simply evaluate from 0 to the natural log of 4. So when we put in natural log of 4, e to the natural log of 4 is just 4. 4 times 8 is 32. So 32 pi right there. And then you put the natural log of 4 in here. Now think about this. 2 natural log of 4. You see that 2? It comes up here on top. That's natural log of 16. E to the natural log of 16 is just 16. So 16 over 2 is 8. So minus 8 pi. Okay, so that's when you plug in natural log of 4. Now you subtract off what happens when you plug in 0. Now when you plug in a 0, you're going to get 8 pi. You get 8 pi, because this 0 is going to be 1, right? E to the 0 is 1, so you just get 8 pi right there. Plug in a 0 here, that's e to the 0, that's going to be 1, so just minus pi halves. Alrighty. Okay, and so that gives you 32 pi minus, so 32 pi minus 8 pi and minus another 8 pi, that's 16 pi. But then 16 pi and then plus a pi halves because the negative distributes. So 16 pi plus a pi halves. And 16 pi is the same thing as 32 pi halves. So it'd be 33 pi halves. Okay, so the volume is of the rotated region is 33 pi halves. Okay, and that finishes us off on that example. Thanks for watching.